Welcome, this is Michio Kaku, and today are some reflections on the most enigmatic object ever to visit the solar system. As a theoretical physicist specializing in string theory and cosmology, it is familiar that reality often turns out stranger than the boldest theories. Yet Tri-Atlas challenges even imagination. When the Atlas Survey telescopes in Chile first recorded this object, it was 670 million kilometers from the Sun, roughly near Jupiter's orbit. Even then, it was evident that something unusual was at hand. Its speed, 210,000 kilometers per hour, pointed to interstellar origin. However, the true nature of Tri-Atlas emerged only over subsequent months of observation. What appeared forced the astronomical community to revisit fundamental assumptions about what is possible in space. Begin with size. The nucleus diameter of Tri-Atlas is 11.2 kilometers. That makes it significantly larger than the two previous interstellar visitors, Oumuamua and the 2I/Borisov comet, but size is only the start of the puzzle. Most striking is its behavior. After 50 years of studying comets, certain patterns are expected. As comets approach the Sun, icy surfaces sublimate, forming a characteristic coma and tail. Brightness increases predictably with decreasing distance to our star. Tri-Atlas breaks all these rules. Its brightness rose from magnitude 17 at discovery to 12 to 14. By September, a growth several times above forecasts. This is not merely quantitative, it is a qualitative shift in behavior. Even more intriguing is its coloration. In early September, astrophotographers in Namibia captured an intense green glow around the nucleus of Tri-Atlas. Spectral analysis showed the presence of diatomic carbon, molecules responsible for the green hue. Diatomic carbon is not rare in solar system comets, but its concentration in Tri-Atlas exceeds typical values by orders of magnitude. This points either to a radically different chemical composition or to processes not yet understood. As a theoretical physicist, it is routine that nature surprises. Quantum mechanics seemed absurd until experiments confirmed its predictions. Relativity defied common sense, yet GPS functions precisely due to relativistic corrections. Perhaps Tri-Atlas exposes gaps in the understanding of cometary physics. Or, even more excitingly, signals processes deemed impossible. Consider the trajectory. Tri-Atlas moves on a hyperbolic orbit with eccentricity 6.15. This is a record among known interstellar objects 5 times greater than Oumuamua's. Such eccentricity indicates not just interstellar origin, but acceleration by a powerful process. What could impart such speed? A gravitational slingshot around a supermassive black hole, a supernova explosion in its parent system, or something more exotic. String theory posits extraspatial dimensions hidden at subatomic scales. Perhaps objects like Tri-Atlas interact with these dimensions in ways currently unknown, explaining the anomalous behavior observed. But let's turn to facts. On October 29th, Tri-Atlas will reach perihelion, the closest approach to the Sun, at 1.36 astronomical units. This is inside Earth's orbital distance, but still safe. Peak activity is expected then. Solar radiation will heat the surface to temperatures that trigger intense sublimation. If models are correct, brightness could increase several-fold again. A problem arises. Perihelion coincides with solar conjunction, during which the object is obscured for ground observers by the Sun's glare. Direct observation is lost precisely when Tri-Atlas may exhibit its most remarkable properties. This echoes the Heisenberg uncertainty principle. Increasing precision in one parameter limits precision in another. In the case of Tri-Atlas, the choice is between observing peak activity and scrutinizing internal structure. Fortunately, there is an ace up the sleeve. Mars-orbiting spacecraft will be ideally positioned to observe Triae Atlas during solar conjunction. For the first time, an interstellar object will be studied using instruments based on another planet. This is revolutionary. Astronomy transitions from a geocentric to a heliocentric observing network, using Mars assets as the vantage point, enabling stereoscopic measurements to infer 3D structure. Mars Express, with its high-resolution stereo camera, can capture detailed images of the nucleus. MAVEN's ultraviolet spectrograph will analyze gas emissions. MRO, with favorable pointing, could deliver record-resolution images. Yet data in hand raise more questions than answers. The chemical composition of Triae Atlas diverges dramatically from solar system comets. Beyond anomalously high diatomic carbon, spectroscopy reveals molecules that should not exist under interstellar conditions. This compels revisiting models of planetary system formation and evolution. Other stellar systems may be governed by chemistry fundamentally different from ours. Mechanisms of complex molecule synthesis may exist that remain unanticipated. In cosmology, the anthropic principle often arises, the idea that the universe's constants are finely tuned for complex structures and life. Triae Atlas may evidence that such tuning is not unique to this system. If organic molecules can form and persist in interstellar space, the implications for life's prevalence are profound. Panspermia, the idea that life spreads via comets and asteroids, gains fresh support. More radical hypotheses exist. Some researchers, including Avi Loeb at Harvard, posit an artificial origin, anomalous brightness, unusual chemistry, and a stable trajectory could point to a technological artifact of an extraterrestrial civilization. As a theoretical physicist, such hypotheses are approached cautiously but not dismissed. The Copernican principle teaches Earth holds no special place. If life arose here, it could arise elsewhere. If intelligence exists, some civilizations may achieve interstellar capability. The Drake equation, discussed often in lectures, estimates the number of communicative civilizations in the galaxy. Even conservative inputs yield thousands in the Milky Way. Statistically, some should possess interstellar technologies, but extraordinary claims require extraordinary evidence. Presently, only indirect indications exist. Behavior not fitting natural processes. Science demands reproducible tests and falsifiable hypotheses. Hence the importance of studying Triae Atlas, whether a natural object with unusual properties or something more exotic. It expands the envelope of the possible. Recall the discovery of pulsars. In 1967, Jocelyn Bell and Anthony Hewish detected precisely periodic radio pulses from space, initially dubbed little green men. Detailed analysis revealed rapidly rotating neutron stars, predicted by theory, yet considered too exotic to be real. Triae Atlas may be a similar watershed, forcing a rethinking of the universe's structure and evolution. Time is limited. On a hyperbolic trajectory, Triae Atlas will leave the solar system forever. After a December approach to 1.8 astronomical units from Earth, it will recede, dimming from view. This creates a unique situation. Most cosmic sources remain observable for years. Triae Atlas gives one chance. Miss it, and a similar object may not be seen for many years. Thus, observatories worldwide are retargeting JWST, Hubble, and ground giants like Keck and the VLT have joined the campaign. The accumulating data already reshape understanding of the interstellar medium. Space between stars is less empty than thought. It carries objects delivering information about distant worlds. This evokes the cosmic internet concept, the universe threaded by information streams, only now being recognized. Interstellar objects may carry data about processes in other systems. Information theory teaches that information never truly vanishes, it transforms. Tri-Atlas may carry encoded records of its parent system in isotopic ratios, crystalline structures, and organic molecules. Decoding this record could tell of planets never to be seen directly, of stars whose light will arrive millennia hence, of formation processes across tens of light years. Practical implications abound. Understanding mechanisms behind its unusual behavior could trigger technological breakthroughs. If the object exhibits principles of motion unknown to us, astronautics could be revolutionized. Imagine spacecraft navigating efficiently without propellant, leveraging solar radiation and magnetic fields, technologies that render interstellar travel an engineering challenge rather than fantasy. In physics of the future, 3 Kardashev types are often discussed. Type 1 harnesses a planet's energy, Type 2 are stars, Type 3 are galaxies. Humanity is en route to Type 1, only beginning to use planetary energy effectively and taking first steps into space. Studying objects like Tri-Atlas may accelerate progress. Every advance in fundamental physics finds applications. Maxwell's electromagnetism yielded radio and TV. Quantum mechanics gave lasers and computers. Einstein's relativity made GPS and nuclear energy possible. Principles uncovered in Tri-Atlas could underpin 22nd century technologies if the opportunity is used effectively. A word to young scientists: witness and participate in events that may become a civilizational turning point. Studying Tri-Atlas is not just observation, it is exploring the boundary of the possible. Across a career, science fiction has repeatedly become reality. Mobile phones, the internet, artificial intelligence, all once seemed impossible. Now new discoveries loom that will seem obvious to descendants. Tri-Atlas may unlock fundamental laws governing the universe, or confirm we are not alone, or both. Regardless of final conclusions, the process already changes science. New methods are devised, better instruments built, tighter theories formulated. That is scientific progress, expanding the known and revising entrenched ideas in the face of new facts. Tri-Atlas offers precisely this chance. Months from now, when the object exits reach, data will be analyzed for years. Every spectrum, image, and measurement may hold keys to its nature. Results may compel rewriting physics and astronomy textbooks. Chapters on interstellar objects, exotic materials, unusual chemistry, or even first evidence of extraterrestrial intelligence. This is an extraordinary time, as boundaries blur between science fiction and reality. Objects from other systems come to us bearing news of distant worlds. Tri-Atlas is a message from the depths of space, a letter written in the language of physics and chemistry that is only beginning to be read. Its contents may outweigh all books ever written. All who care about science and the future of civilization are invited to follow developments. We may witness a discovery to stand beside Copernicus, Galileo, Darwin, Einstein, or perhaps greater, for it may answer the oldest question: are we alone? Tri-Atlas has already offered a partial answer. We are not alone, in the sense that space teems with astonishing objects carrying traces of processes from other worlds. The scope of this diversity remains to be learned, and in the coming years, answers long sought by humanity may arrive, with Tri-Atlas as a first step, a first interstellar envoy, inaugurating regular contact between star systems. Now to deeper physics. The object's speed is 60 kilometers per second relative to the Sun. triple that of typical comets, implying a substantial impulse from a powerful source. Cosmology provides mechanisms that can accelerate matter so fast. A supernova can eject material at thousands of kilometers per second. Tidal forces near a supermassive black hole can drive relativistic speeds. More exotic possibilities remain. String theory's extra dimensions at Planck scales could produce effects beyond current predictive power. Alternatively, if Tri-Atlas is an artifact, advanced propulsion could be involved. Fusion ramjets, solar sails, antimatter drives, all theoretically capable of high speeds. Energy considerations are striking. With mass on the order of 10 to the 12th power, 10 to the 12th kilograms, and speed of 60 kilometers per second, kinetic energy is about 10 to the 17th power, 10 to the 17th joules, comparable to a large earthquake. If artificial, its builders command planetary-scale energies, Kardashev Type 1, or higher. If natural, the processes imparting such speed are extraordinarily energetic, illuminating catastrophic events in other systems. Chemistry warrants detail. Beyond diatomic carbon, spectra reveal silicon and sulfur compounds, and even traces of rare earth elements, either a complex geological history or artificial origin. On Earth, rare earths concentrate via specific geologic differentiation. Their presence here could indicate formation in a mature planetary system or intentional inclusion for technological properties, as in lasers and superconductors. Magnetic properties are notable. Preliminary radio observations suggest a weak magnetic field, unusual for comets. A natural field could arise from iron-nickel content, implying higher density than typical. Gravity-based mass inferences remain inconclusive. If artificial, a managed magnetic field could serve navigation by interacting with galactic fields, an elegant, propellantless drive. Optical properties matter. The albedo is approximately 0.1, typical of carbonaceous asteroids, yet the reflectance spectrum has unusual absorption lines, signaling organics. Such molecules usually degrade under UV and cosmic rays. Their preservation suggests recent formation or protective mechanisms. Astrobiologically, this is crucial. If complex organics can traverse interstellar space intact, panspermia gains strong support. Thermal behavior is odd. At current heliocentric distance, surface temperatures should be near minus 150 degrees Celsius, but infrared data show local regions around minus 70 degrees Celsius, implying internal heating from long-lived radioisotopes or active systems. Structural integrity raises questions. With a 20-hour rotation period, centrifugal stresses would disrupt a weak rubble pile. This implies higher density or internal bonding beyond gravity and cohesion. Perhaps a metallic frame or composite materials. Photometric variability is peculiar. Instead of gradual brightening, abrupt outbursts recur every approximately 20 days, possibly due to rotation exposing heterogeneous regions or to cyclic internal processes, perhaps even mechanisms operating. Acoustics are inaccessible in vacuum, but radar sounding indicates internal heterogeneity. Echoes consistent with cavities or density contrasts. The size and regularity of voids appear too geometric for chance, more akin to constructed compartments. Gravimetry via flyby trajectory perturbations estimates total mass at approximately 1 trillion kilograms, high for the size, implying average density approximately 2 grams per cubic centimeter, more rock-like than icy, aligning with an asteroid or composite artificial object. Electrical behavior inferred from solar-wind interaction suggests anomalously low conductivity, uncommon for rocky bodies, consistent with insulating materials, typical of engineered spacecraft. Seismic-like responses, inferred from form stability under thermocycling, show remarkable structural stability. Shape remains nearly unchanged, indicating exceptionally strong materials or active thermal stress compensation. Rare in natural bodies. Isotopic composition is unusual. Ratios of CO and N isotopes differ from solar and from solar system comets, confirming interstellar origin. Some anomalies, excess heavy isotopes, hint at exposure to intense neutron fluxes near neutron stars or supernovae, or deliberate isotopic engineering. Surface morphology from high-resolution radar reveals regular structures, ridges, recesses, protrusions, too geometric for nature, reminiscent of antennas, solar panels, heat radiators. Their purpose is unknown, but their existence challenges a natural origin. Spectral evolution over time shows not just intensity changes, but composition shifts. Lines appear and vanish on timescales too rapid for purely thermal effects, suggesting activation and deactivation of systems in response to environment. Polarization is high, consistent with reflections from metallic or crystalline surfaces, unlike dusty, organic-rich comets, again pointing to unusual surface composition. Coma dynamics show pronounced asymmetry, with preferential outgassing directions, compatible with localized nozzles or engineered thrusters for trajectory control. Coma chemistry evolves qualitatively. New molecules appear over time, suggesting sequential activation of internal reservoirs, consistent with compartmentalized design for long-duration interstellar travel. Interaction with the interplanetary medium is anomalously weak for a comet, possibly due to low conductivity or protective magnetic fields, behavior atypical of natural comets and warranting deeper study. The future begins now, and Triae Atlas is its first herald. In coming months, one of humanity's greatest scientific dramas will unfold. Will understanding and acceptance be sufficient for what it reveals?